Good morning, students. Yesterday we discussed the method of successive approximations and derived the Newman series. Today we will discuss the conditions for the convergence of that series. So, in order to discuss the conditions of convergence for the Newman series, let us consider the general term of Newman series. The general term of Newman series is integral kmst ft dt. We consider the square of mod of this term. Here km is the mth iterative kernel, which we have already studied. Now considering this term and applying the squash inequality. By using squash inequality, this term can be written as this is less than or equal to integral kmst mod square dt into integral ft mod square dt. Now let us take d is the norm of the function f. Norm means the square root of inner product of the function with its conjugate. So by definition of norm, d is the square root of integral ft mod square. Now therefore d square will be integral ft mod square dt. Also let us take an upper bound for integral kmst mod square dt. Its upper bound we have denoted by the symbol cm square. Now substituting these two values in the equation 1 here, because this has the upper bound cm square and its value is d square. So substituting the values, we get integral km st ft dt mod square is less than or equal to cm square into d square. Now let us connect the term cm square with c1 square. So in order to connect these two terms, let us consider the square of the mod of the mth iterative kernel. Here km is the mth iterative kernel. So by definition of mth iterative kernel, it is given by k m minus 1 sx kxt dx. Now we consider the square of mod of this integral by using the squash inequality again. This is less than or equal to integral km minus 1 sx mod square dx into integral of square of mod of kxt dx. Now again by using this notation, we have taken cm square upper bound for this integral. In the same way, for km minus 1, we have the upper bound cm minus 1 square. So using again this notation, this is less than or equal to cm minus 1 square, and this term we have kept as it is. Now we have obtained the square of mod of mth iterative kernel is less than or equal to cm minus 1 square into integral of square of mod of kxt. Now let us integrate both sides with respect to t. So integrating both sides with respect to t, we get integral kst mod square dt is less than or equal to cm minus 1 square and double integral kxt mod square dx dt. Now let us denote this term by b square. So using this notation, here the term becomes integral kst mod square dt is less than or equal to cm minus 1 square into b square. So this further implies that because cm square is the upper bound for the mth iterative kernel, so therefore we have cm square is less than or equal to cm minus 1 square into b square. Now substituting m is equal to 2 here, we get c2 square less than or equal to c1 square into b square. If we put m is equal to 3 here, we get c3 square less than or equal to c2 square into b square. Now because c2 square is less than or equal to c1 square into b square. So substituting the value here, this will be less than or equal to c1 square into b square into b square. So we can say that c3 square is less than or equal to c1 square into b raised to the power 4. So continuing like this, in general we get cm square is less than or equal to c1 square into b raised to the power 2m minus 2. Now again from the equation star which we have taken already, in that equation integral km st ft dt mod square is less than or equal to, in that equation we will replace cm square by this term. After replacing cm square by this term, we get this term less than or equal to b raised to the power 2m minus 2 into c1 square into d square. Now taking positive square root on both sides, so taking positive square root in this term becomes this, and here after taking positive square root we are left with b raised to the power m minus 1 into c1 into d. Now in the method of successive approximations we had derived Newman series. So in the Newman series, taking mod on both sides, taking mod of gs, where gs is the solution of Fredholm integral equation of second kind, taking mod on both sides, and here by using the triangle inequality, this is less than or equal to fs mod plus here again this is less than or equal to lambda mod raised to the power m integral kmst ft dt mod. Now this is further less than or equal to fs plus here that term is replaced by using the equation 5. From the equation 5 the expression is less than or equal to b raised to the power m minus 1 into c1 d. Now expanding this summation here, m is equal to 1, 2, 3. Inside of the brackets we get a series which is a geometric series, and we know that a geometric series is convergent if the common ratio of the series that is less than 1. So here the common ratio of this geometric series is obtained by dividing this term by this term. So if we divide this term by lambda mod, the common ratio is lambda mod into b. So this series will be convergent if this common ratio is less than 1, or we can say that lambda mod is less than 1 upon b. So this is the condition of convergence for the Newman series. Now the next topic is the uniqueness of the solution of Fredholm integral equations of second kind. So we'll prove that if we are given Fredholm integral equation of second kind, which is gs is equal to fs plus lambda integral kst gt dt. Here the limits of integration are a to b, which we have omitted in the notation, and lambda is given. We have to prove that the solution of this Fredholm integral equation is unique. In order to prove the uniqueness of solution, let us consider two solutions. One solution we have taken g1s, and other solution we have taken g2s. So we have taken two solutions for this integral equation because g1 is the solution of this integral equation. So here replacing g by g1, because g1 is solution, so that will satisfy this integral equation. So here replacing g by g1 we get g1s is equal to fs plus lambda integral kst g1t dt. Also the function g2, that is also the solution of given integral equation. So the given integral equation will be satisfied by g2. So in this integral equation replacing the function g by g2. So replacing function g by g2 here we get g2s is equal to fs plus lambda integral kst g2t dt. Now let us subtract these two equations. When we subtract these two equations we get g1s minus g2s is equal to, here after subtracting we get lambda integral kst g1t minus g2t dt. Now the difference of g1 and g2 that we have denoted by a function phi, because that is the function of s, so we have denoted it by phi s. Now using the notation here we get this equation, and here also g1s minus g2s that we have denoted by phi s, so this will become phi s. Here we get lambda integral kst, this is phi t dt. Now taking mod on both sides and then squaring, we get lambda integral kst phi t dt mod whole square. Now this is further is equal to lambda mod square into the square of mod of integral kst phi t dt. Now again by using squares inequality, this will be less than or equal to lambda mod square into integral kst mod square dt into integral of square of mod of phi. Now integrating both sides with respect to s, so on the left side integrating we get integral phi s mod square ds. Here also integrating with respect to s we get this term. Now we have used the notation for this as b square, so that term is replaced by b square. So we get, now shifting this term on the left hand side, we get integral phi s mod square ds into 1 minus lambda mod square b square. This is less than or equal to 0. Now in the conditions of convergence we have studied that lambda mod b, that is less than 1, so it cannot be negative, this term cannot be negative, also this term is non-zero. So and also this is norm of the function phi and its square, so norm is also non-negative, so that cannot be negative. So only possibility is that this term integral phi s mod square ds, that will be 0. Now because this function is non-negative function, so if its integral is 0, then the function phi, that will itself be 0. Now phi is 0, phi means g1s minus g2s, so that will be 0. It means g1s is equal to g2s. So we have taken two solutions, g1 and g2, for the given Fredholm integral equation of second kind, and we have shown that the two solutions are same. So thus we have proved that the Fredholm integral equation of second kind has a unique solution. So this proves the uniqueness of the solution for the given Fredholm integral equation of second kind.